Okay, well, welcome everyone. And we're here on behalf of the Illinois Math and Science Academy and the Jimbo collaboration to present our results for a search for unparticles and DDKs, proton-proton collisions at 20 TeV.
Hi, my name is Ivan. I worked in the theory department of this, so I dealt mainly with what exactly is this. So first we have to start by asking, what exactly makes a particle a particle? Well, any basic physicist is going to know that E squared equals m squared plus p squared, and that's one of the fundamental laws of physics. Now, at any point in the space-time continuum, this is going to hold true. But what happens if your mass changes? So if your mass changes, then your momentum is going to have to change accordingly if you have the same energy. But the more important factor is that if your mass changes, you no longer have the same particle, and the physics of an interaction with this particle are not going to be the same. So what does that mean? Well, one of the key parts of Georgi's theory is scale invariance. Now, scale invariance, it means that all quantities can be scaled by some constant lambda raised to a mass dimension without changing the physics. Well, if we look at E squared equals m squared plus p squared, like we were saying before, if we change the m, then we're no longer getting the same particle, and thus the physics are not going to be the same. So therefore, we can include the standard model cannot be scalar invariant for standard massive particles. Georgi asked, unparticles. Just what exactly does the scale invariant theory look like? Well, he first starts off with his general coupling. So we see there's two parts of this, the standard model field and the Banks-Zach field. Unfortunately, this is only going to couple at very high energies, and that is because the mass scale theory suppresses those energies and suppresses the coupling between them unless they're at very high energies. And we don't know exactly what these interactions are going to look like at these high energies. One key thing to note, though, is the Banks-Zach field has some point, it's non-trivial IR fixed point, at which below it is scale invariance. And we can use this and renormalization to determine the interactions with unparticles. So if you look here, this is one example of what scale invariance and renormalization looks like. So renormalization is scale variance, and then equations like the above hold true. And that allows us to look at these unparticle interactions and use effective field theory to determine the physics in the scale invariant low energy limit. So if we go back, this is what the equation looks like now. Now, first of all, notice that the Banks-Zach field has turned into the unparticle operator. And this is because below this infrared fixed point, the unparticle operator matches up to this Banks-Zach theory because of scalar invariance. So, assuming that we have this scalar invariant fixed point, we were able to calculate with the low energy field what exactly the interactions will look like. And this allows us to calculate the phase space of unparticles.
My name is Cecilia, and I worked alongside Evan in the theory department. So since we don't know anything about unparticles, we try to assume as little as possible in the theory. So Georgi figured out that the general form of the phase space for unparticles by applying the scale invariance to the general unparticle matrix element, and he gets this equation. And this equation is the exact same equation as the phase space for n massless particles, but instead of n, we have du. And unlike n, du has to be could be a fraction. And so we figured out that unparticles with a scale dimension of du will look like a fractional number of massless particles.
So I'm Matt, and I was in phenomenology, and I looked at event signatures. So for the unparticle, there are several events that we can look at: monojet, monophoton, Drellian, and ZDK, and fermion, anti-fermion, and unparticle. So monojet events are possible at hadron colliders and are really clear and easy signatures. However, the phase space of du is drowned out because of all the other jets that happen at hadron colliders. In monophoton events, they're electron-positron. They're really easy to find at electron-positron colliders, and they're also really clear signature like the monojet events, but they're not practical at hadron colliders and really most other colliders because we can't build a collider to get positron and electrons to a high enough energy because of synchrotron radiation. In the Drellian process, which is photon decay into positron and electron, has a really clear interference effects that are sensitive to the anomalous dimension near the Z mass. However, there are a lot of experimental uncertainties with the Drellian process, so it's really difficult to observe. For the Z decay, it's also a clear signature, really well studied as well. However, it has to be disentangled from really the standard model predictions. So branching ratio. So So this is the main branching ratio, and then the drift branching ratio. X1 represents the fractional energy from the Z particle that goes into fermion. X2 is the fractional energy of antifermion, and then the Z is the fractional energy of the particle.
So I'm Ioana. I also worked in the Phenomenology department, except I worked with an anomalous dimension. And so what it actually does, it measures the rate normalized behavior, which depends on it, but the anomalous dimension is also known as the beta function. So as a whole, within the beta function, you have the coupling constant, which is actually related to it, and it actually scales everything down, which depends on Q squared, which is the energy of the entire thing. And then within the Banks-Sachs theory, this constant will then at one point remain constant even as the energy changes. So when you look at the actual calculations with this, is the first equation up on the top, the ADU, is the entire calculation we're looking at, but within it that depends on GU. But because we don't know the value of GU, we have different possible values we can get, and using that value of ADU we can then calculate the decay width, which is the first graph on top. But using the possible values we can get, because we don't know what X1 really is either, which is the energy fraction of the fermion, which there can be different possible values of. We use those values and the information we get from the GU statistics to integrate the possible values of sheet.
Hello, I'm Carolina. I worked on the accelerator design. So to set up this experiment, we had to design an accelerator and a detector. The important part about the accelerator design was that we had to have a high energy collision with high luminosity, and for the detector to have a very precise energy measurement with good angular resolution and fast electrons. We went with a proton-proton collider because we thought it would be easier to maintain that high luminosity that we need. Our accelerator complex begins with a LINAC that accelerates the beam to 50 MeV. Then we insert into one of 4 boosters. The first two accelerate the protons first to 1.4 GeV, then to 26 GeV, using conventional magnets with a magnetic field just under 1 Tesla. And then we have the next 2 boosters that accelerate to 450 GeV and then to 1 Tesla using superconducting magnets. At 1 TeV, we inject into the collider, which is 4.5 kilometers in radius, and that accelerates each beam to 10 TeV, giving us a total energy at collision of 20 TeV with a bunch crossing rate of just over 40 megahertz.
So this is just like an overview of what our entire detector looks like. And my name is Stoyan. I worked in the tracking working group. And the design of our tracker with a solenoid field of 4 Tesla, it contains 2 layers of pixel detectors, which are located at a radius 30 and 40 millimeters, and 3 layers of double-sided microstrip sensors, which are located at radius 50, 70, and 90. We have a total of 1,100 strips, 300 within the first layer, 360 within the second, and 440 in the third. Our design does not include end caps because the chamber is really thin, as you can see, with only a max radius of 90 millimeters and long enough, a length of 7.7 meters, that the angular acceptance is 99.263%, which means that there's a very small chance that something won't go through all the layers. And the momentum measurement is at a lower priority here than our energy measurement. And the algorithm that we use to calculate this, basically we take the coordinate plane and divide it into 4 quadrants, and each quadrant is divided in 3 sectors along the z-axis. And if 2 tracks are still indistinguishable within these parameters, then these sectors will collapse and continue to be subdivided until we can make a distinction. And as you can see again, the angular acceptance is very high, so there's little that can go through.
I'm George from the Calorimeter working group. one of the key components of detecting unparticles is a very high energy resolution. So that's, given our very large cavern space, we were able to use that to design a very large and very accurate calorimeter system. So here our shaded electromagnetic calorimeter weighs in at 0.6 meters thick, and it has the accordion partitioning scheme so that there are few cracks between the layers as possible. Our Donner hydronic calorimeter weighs in at 6.7 meters thick and has a very, very, very accurate 512 sector partitioning scheme, so we have a very good angular resolution. The eta for the hydronic calorimeter is every 0.1 eta, starting at 0.05 eta. Both of these calorimeters use bismuth silicate scintillator for its high accuracy or high sensitivity, as well as its very fast decay time. Steel observer for its long interaction length and therefore low absorption and energy loss, and how it amounts to 256 channel PMTs as part of our scintillation scheme in the next slide. Furthermore, the hydronic calorimeter is disproportionately larger than the electromagnetic calorimeter because our focus is on Z into fermion decay, so jet detection. So our scintillation scheme is called superb accuracy through rapid scintillation, or SARS. And the idea is that if we can place as many scintillation layers as possible for interaction length, we can increase accuracy. Obviously, this results in a huge number of fibers, which we solve using optical multiplexing. Basically, each scintillation layer has a wavelength shifting fiber so that the frequency of light coming from the layer is able to be shared within each cable. We're able to put 20 channels per cable, which are unmixed at the end using diffraction grading and fed into our 256 channel PMTs. This allows for 1 millimeter scintillator for every 1 millimeter absorber, which is 3,350 scintillating layers per tower with only 14 PMTs. Oh, and also our clustering algorithm. We would identify clusters by looking for peaks within our calorimeter and then expanding outwards from those clusters to identify the range.
Hello, I'm Austin from the Muon working group. So the Muon system of Jimbo is the outermost layer. It has a diameter of 6.55 meters around the outside and consists of 8 air core toroids, which are equally spaced, arranged octagonally. Each of those has a diameter of 0.5 meters. The Muon will be spending about 4 meters of its flight path inside the air core toroid. There's a 5 centimeter lead shielding in between the inside of the Muon detector to reduce punch through of other particles. There are 6 layers of monitored drift tubes throughout the Muon system. There are 2 at in the inside edge of the Muon system, 2 inside the air core toroid, and 2 on the outside edge. There are 2 layers of resistive plate chambers, which are used for triggering. There are circular end caps, which are used to catch any muons that end up going straight through. So the path of a muon through an air core toroid, as the muon leaves the event site, it travels in a straight line path until it reaches the magnetic field, which is generated inside the air core toroid, which peaks at 4 Tesla. The path of the muon will then bend as it moves through the field, and as it exits the toroid, will resume its straight line path. So we can see there are kinks in the path where the muon enters and leaves the toroid, as demonstrated by this graph. So the tracking algorithm takes the fact that we have 3 separate layers of detectors on the inside edge, the outside edge, and in the middle. We define curves, 3 separate curves, 2 straight lines on the inside and outside edge, and then a curved path inside the toroid. By connecting these, we can find the paths of each muon and then calculate their momentum.
Hi, I'm Auden from the trigger working group. Here's a basic outline of our trigger system. So as you can see, it goes through a hardware trigger, 1 level of hardware triggers into a level of software triggers, which is reconstructed by the event builder, and then goes into another level of software triggers. So for our hardware triggers, we have 1 level made up of the different parts that you can see here. We chose to have a 60 event buffer for the level 1 buffer, as our event rate in is 40 megahertz, and our event rate out from the hardware trigger will be 100 kilohertz. We have 2 levels of software triggers made up of the parts you can see here. The events that pass through at the level 2 software trigger are reconstructed by the event builder and analyzed by the level 3 trigger. So we chose to have a 5 event buffer for the level 2 triggers. The event rate in is 100 kilohertz in and 5 kilohertz out to the level 3 trigger. And the event rate in for there is 5 kilohertz and 200 hertz out to storage. So the specific event signatures that we were looking at for triggering were the 3 types of events that we're looking for, which were Z boson decay into quarks into 2 jets, into electron and positron, and into muon and anti-muon. So for going Z boson decay into jets, the level 1 required a high transverse energy cluster, the level 2 required 2 high transverse energy clusters, and the level 3 required 2 reconstructed high transverse energy clusters. For electron-positron, the level 1 required a high transverse momentum track and a high transverse energy cluster. Level 2 required the track to point at the cluster, and level 3 reconstructed the event and required the track to be isolated. For decay into muon antimuon, it was a similar way to the electron-positron, except they used a muon stub rather than a high transverse energy cluster.
Hi, I'm Colette, and I was part of engineering. So for the cryogenic system, we used liquid helium, which we were cooling to 1.5 Kelvin so that it would act as a superfluid and offer no resistance. To do this, we ran a line for it straight down at Z equals 0 to all the way down to the solenoids. And then for the power cables, we ran them through at 45, 135, 225, and 315 degrees to get power all the way to tracking the center. And to do that, we weaved the cables all the way through the muon system, and then we would take one of the wedges from the hadronic calorimeter up to put cables through, and then we cut through the solenoid all the way to tracking so we could get power then. We also ran cables out along the beam pipe so as to more evenly distribute where the cables went. For the support structures, we mainly used carbon fiber, but for some of the heavier bits that were more iron, we used steel support structures.
Hi, my name is Luton, and I work in the Lepton group. And so when we were identifying leptons, we wanted to obviously eliminate as much background as possible while keeping as much signal. And so what this means for electrons is that we have to eliminate the jets, which fake the presence of the electrons. And for muons, we have to eliminate pions and kaons or hadrons, which punch through all the way to the muon detector. And so for the electrons, we use isolation, which is a variable, which is basically the ratio of the transverse energy outside of the lepton cluster to the energy on the inside. And for jets, this ratio is really high, and for just electrons on themselves, it's going to be really low. And so this histogram is actually a graph of for isolation, and out of 1,000 events, we only had one event that go over 0.1. So this is a very good cut. Another cut we used was the ratio of hadronic energy to electromagnetic energy, and we used 0.05. And the reason we use that is because electrons leave very little energy inside the hadronic calorimeter, and jets leave a lot. So that was a really easy cut. For muons, we used the values of 2.0115 GeV and 6.028 GeV because muons are minimum ionizing particles, so they only need very low energy, as opposed to jets, which would have energies much higher than this.
Hi, I'm Joseph. I worked on identifying the identification efficiency of Moulton's algorithm. So taking the data of which events Moulton identified as true and just background of leptons, I decided to take a mass cut around the Z boson to get a pure sample of the decay of a Z boson into an electron and a positron. Analyzing the data sample, I found 84 cases where both leptons were had the same sign, which provided the background, and then using that estimate, I found the false positive rate and applied that to the data sample to eliminate an estimated number of events, and then calculate an identification efficiency of 88.62% for the data. And comparing that to a Monte Carlo simulation that we use to estimate properties of the interaction, I performed a similar mass cut and then calculated the identification efficiency, knowing this time there's no background. And then calculating the ratio of the two identification efficiency rates, I calculated a scale factor of 99.13%.
My name is Hope, and I worked with the jet energy scale correction factor.
specifically looking at the pseudo-rapidity and the calorimeter scale factors. So we began examining the pseudo-rapidity dependent correction factors by examining 1,000 dijet events, and with a good separation of energy and trigger levels. Since we knew that the transverse momentum had to add up to 0, we were able to then know that the ratio between the two jet events had to be 1. So then we separated each of the dijet events into bins of different pseudo-rapidity values, and then found the correction values for each bin, as we can see to the table to the left. And the figure to the right just shows the different ranges of the pseudo-rapidity values. In addition, the calorimeter response correction factor, we had to find the correction factor that basically helped with the response of the calorimeter values that were not detected by our detector. And we use the following equation up there, specifically looking for the two factors of the jet response and the uncertainty factor. The jet response was taken using the calorimeter's average energy value over the particles' average energy values, in which we found to be 0.931. And the uncertainty factor, since we knew the different energy values, we could then take that ratio, and we didn't know the momentum, so then we had to basically use our knowledge off of the mass of a proton as well as the energy values to get the following calorimeter correction factor.
My name is Cameron Hudgens, and I'm here to talk about event selection. So first of all, we were trying to eliminate QCD multi-jet events. And to do this, we needed to eliminate them at a very high rate, and this requires a very hard cut. So we only considered events that had a leading jet transverse energy greater than 60 GeV and a second jet transverse energy greater than 21 GeV. This allowed us to keep 60% of the original signal while only maintaining 0.7% of the background. As for electrons, we were trying to eliminate the W plus jets events. To do this, the electrons must have opposite signs. In this case, we were only considering events that had a leading electron transverse momentum greater than 70 GeVC and a second electron transverse momentum greater than 35 GeVC. And this allowed us to preserve 52% of the original signal, while only 12% of the background passed the cuts. As for muons, we were trying to eliminate punch-through pions and kaons. To do this, we were only considering events that hit all 6 of our muon layers. This allowed us to preserve 90% of our signal, and only 0.1% of the background events passed the cuts.
Hi, I'm Jeremy. I was responsible for Luminosity. And so the name of my luminosity detector was called Cloud, which stands for Turing Gauss Luminosity Over Under Detector. And so it's similar to the lucid detector, and there are 2 monitors, one on each side of the interaction point, placed 2 meters away. Each monitor has 5 Turing Gauss detectors, each being 2 centimeters in diameter and 2 meters in length. And these are accompanied by identical sized photomultiplier tubes. And then there's also recirculating perfluorobutane gas system because of the high luminosity. For the measurement, I found the average events per collision to be 9.543. And then the frequency that our glider runs at is 40,900,000 hertz. And then to get the cross-section, I extrapolated from the Tevatron using a linear relationship to find it to be 51.1 millibars. And in using this number, or using these, I found the luminosity to be 7.47 times 10 to the 33rd inverse centimeter squared inverse seconds. And then after this, I was given a store where luminosity was measured once per second over an entire day. So then I calculated the entire luminosity per day and the entire luminosity over a year. And using this, I calculated the integrated luminosity to be 17.77 inverse femtobars.
Hello, my name is Jack Mueller. I work for the Analysis Working Group. So what I did was, given values from my fellow coworkers, what I did was I calculated the signal estimate. And what the signal estimate is it's the number of events for certain parts of the detector. So first we needed to find the total number of events, and what we did was we took a cross-section, which was provided by theorists, and multiplied it by the total luminosity, which was the value that Jeremy calculated to be 17.77 inverse femtobarns. And then we converted the 17.77 inverse femtobarns into nanobarns, so that way we could eliminate barns as a unit by simply multiplying nanobarns by inverse nanobarns. So what we did with the number of events was then we multiplied it by cuts provided by Cam, and then values provided by Joe and Milutin to cut out any extraneous data points, as well as the acceptance value provided by Stoyan. So that way we could cut out any data points which did not go through the detector. And after doing all of this, we calculated that there were about 400 to 450 million events for the jet, and about 16 million events for the electron and the muon, using the same cuts for both the electron and the muon.
Hello, my name is Alan. I worked alongside Jack for the analysis working group. While he worked on the signal estimate, I worked on the background estimate. So we used the same equation to estimate the number of events. So here we have the four main estimated background events. For the TT, you can see that there's a significantly smaller amount of events. That's because in order for this to happen, for this example, the bottom and anti-bottom quarks must be lost in the track. And then for the W plus jets, for this example, the electron and then the jet must fake an electron also. Because jets have all kinds of different signatures, we used a data approach to analyze the scale factor. So to scale the W plus jets, we can see the histogram binned into 5 categories, and then there's the data histogram and the Monte Carlo. So you can see that both of the graphs have a similar overall shape, but the frequency is off. So using the 2 leptons in 1 jet channel, we scaled it with a scale factor of 1.42 to match it, so there's a much better fit. As for the QCD multi-jet, we took the multi-jet enriched data and looked at just one jet events, and then we made cuts so to make it just the one jet events, and then used a guess of 1 megabarn for the cross section, and then using this we found the scale factor to estimate the QCD multi-jet.
I'm Nick, and I also worked in the analysis working group. And in order to distinguish between signal and background, I created a decision tree with 2 cuts. One with transverse mass of 80, so greater or less than, and the other at second jet energy, greater or less than 30. And from these 2 cuts, I created 4 leaves, and by training the 4 leaves, I was able to determine the purity of each leaf, and the highest one being with the pure signal with a jet 2 energy of greater than 30 and transverse mass of greater than 80 with 77.54%.
Hi, I'm Jack. I worked in the statistics group. And so here we have the general event histogram, which shows the comparison of our observed values from our data with expected values that we generated with a systematic uncertainty of 10%. As you can see, there's an excess with the observed values with expectation, and the significance of that is p equals 0.00932 or 2.3 sigma. And in terms of conclusions, this doesn't really mean much because it's not significant enough to determine that there definitely was an effect, but it's point towards the fact that there could have been some. Okay, and now we have the likelihood fit, and I had to do this for the unparticle hypothesis, and I had to do that analysis in the lepton channel since we had to determine the differential decay rate by distinguishing fermions and antifermions. Also had to subtract off the Monte Carlo expectation so we could just look at the events that could have been unparticles. And so
I had to optimize the likelihood of our observation for the parameter du, the anomalous dimension, and then I binned the expectation for the number of negatively charged leptons that could fall within certain energy fraction intervals, and here they're binned on intervals of 0.1 with the expectation versus what we saw in our observation. And the chi-squared probability for the correlation is 10 to the negative 225, which indicates that the unparticle hypothesis was a poor explanation of our data.
Okay, Sam Raucher, also Analysis Working Group. So since we looked at the fit for the unparticle hypothesis and it didn't really fit our data, we decided to go back and look at the invariant masses for all the events. So up here we have a histogram of every event that we detected, and if we zoom in to about 3600 GeV, we find that there's a significant rise in the frequency of detection. Actually has a z-score of about 710, so we're assuming that we found a particle at 3600 GeV that we don't know what it is. We know it behaves like a z-boson. So, in conclusion, we searched for a signature of unparticles with z decays using proton-proton collisions in the Jumbo Collider with a center of mass energy about 20 teraelectron volts. We found a marginally significant excess of events over our expectations, and the most likely value of the anomalous dimension was 2.3. However, the events weren't consistent with the expected unparticle signature. There was resonance that may represent a new particle that decays like a z-boson, has a narrow width and a mass of about 3,632 GeV.